Hi, Beaumont here. This is the first in a series of 4 YouTube videos talking about p-values. What image does the term p-value conjure up for you, I wonder? Well, I think that's a fairly typical response, and hopefully by the end of this tutorial this image will have faded, if only slightly. I must mention that I have made use of some excellent materials available from Professor Chris Wyle's website. Many thanks. So, where do p-values fit in? Well, this is a typical research cycle for quantitative research, and the diagram again being courtesy of Chris Wyle's. Penultimate stage, analysis, and the last stage, conclusions, is where p-values are frequently used to allow the formulation of sound conclusions. However, if p-values are used in isolation, there is a distinct danger of you making erroneous conclusions concerning your research. P-values should always be interpreted in relationship to sample size, power, and effect size measures. Also, you should consider the various assumptions and specific probability distribution that has given rise to the specific p-value or p-values in your research. Now let's consider why people find p-values so difficult and painful. I think there are 3 main reasons. Many introductory books and websites, with the notable exception of Wikipedia, are inaccurate. They provide wrong, ambiguous, and even obviously illogical and conflicting explanations. Secondly, there are 2 different ways of using the p-value, resulting in opposing interpretations of the results. Finally, understanding what a p-value is demands that you understand also probability, random sampling theory, what the statistic is, and finally what a rule is in this situation. All this requires time and effort to understand, and unfortunately only one of them is an easy topic. But me being one never to avoid pain, let's tackle the most difficult of the topics first: probability. Right, a p-value is not the same as a probability. That is an important thing to get through. A p-value is not the same as a probability value. A p-value is a special type of probability. It considers more than one outcome, and it is a conditional probability. So let's see what a probability value looks like. There's 1.25. This is the same as saying you have a probability of 25%, and in the UK this is probably the probability that it's going to rain today. A probability must lie between 0 and 1, it being 0 when the event will never happen, and 1 when it will always happen, when it's certain to happen. Take the example of winning a lottery. If we have a probability of winning it, say of 1 in a million, I think that's 1 in a million, 1 and 6 noughts, we can say that the probability of not winning it is 1 minus that value, 0.9999. So the take-home message is that at any one time all the possible probabilities for all the outcomes must add up to 1. Additionally, we can group sets of outcomes together to form events, which we'll now consider. There we only had 2 possible outcomes. Now we can consider possibilities of several possible outcomes. Remember in doing this, because a p-value is a type of probability that takes into account multiple outcomes. So here is a histogram which represents the scores from an exam obtained from 48 students. You can see that 11 students got 40 to 44%, whereas one very bright student got a mark within the 85 to 90% range. Now we can also think of these bars as representing a set of relative frequencies, which results in the total area being equal to 1. So if this is the case, remembering that the probability of all outcomes at any one time must also equal 1, it sounds like they can be considered as equivalent, and they can be, except the histogram is now called a probability distribution. So now we know we can work out probabilities from a histogram, so it's how we can use this for an event that consists of more than one outcome. Here are our set of scores, but this time I've actually recorded the real values rather than where they lied within a range. Doing this means that the name of the graph changes from a probability histogram to a probability density function. Same idea, but different name. We can represent the values by using the tree method we first used, and it shows there on its side to understand the similarity. We turn it around, you can see it's identical. This time it has many branches and there are different outcomes, and various outcomes can have the same value. For example, 3 of our 48 students may have scored 43%, each with a probability of 1 over 48. Let's consider the probability of getting a range of scores, say a score of less than 45. We know this is equivalent to finding the area A. Similarly, we know that the probability of getting a score of more than 50 is shown by area B. Notice that both area A and area B are considering multiple scores. That is, they are in this instance considering scores more extreme than a given value. We can calculate probabilities, that is areas for A and B, by simply adding up the individual probabilities. And if we consider multiple areas, we can work out the probability of obtaining any score which was more than 45 or less than 50. Important things to remember here are that we can work out probabilities of multiple outcomes simply by adding the individual outcomes together. And the multiple outcomes might represent outcomes said to be more extreme than a specific value. So let's look at this more extreme idea a little more. In this example, we have taken values more extreme than those of approximately a value of 1.9 on the left. So we have values beyond 1.9 in the positive direction and less than minus 1.9 in the other direction. Now the two shaded areas in the picture on the left. So more extreme in this instance means more positive or more negative than 1.9. Taking an example on the right, we can see here we're only considering extreme values on the right hand side of a particular value. But in both these examples we're assuming that the values can continue forever. In the first example in both the negative and positive directions, and in the second one only in the positive direction. Clearly, while the probability distributions have most of the values hunched up, there is a possibility, although in a very small number of cases, a very rare event, we can obtain one of these exceptionally extreme values. Now let's move on to the next aspect of probability, a situation where one event affects another. Such probabilities are called conditional probabilities. So what happens to probabilities when two or more events affect one another? I've taken this example, by the way, from the excellent book by Paul Taylor called From Patient Data to Medical Knowledge, page 160. Say we have 20 people in a room, 8 female and 12 male, 4 of which have beards. From this information we can work out various probabilities. For example, the probability of being bearded is 4 over 20, which is 0.2. And the probability of being male in a room is 12 over 20, 0.6. So, I wonder if we can combine these to say what is the probability of being a male that's bearded in the room. Say we take 0.2 times it by 0.6, we get 0.12. But actually this is wrong, and intuitively we feel that the gender of a person has an effect upon the probability of them being bearded. So how do we take this into account? The simple answer is that we consider the subset of the group that we feel has the effect upon the characteristic. So in this instance we only consider the males. Let's consider the problem in the form of a probability tree. So the first branch gives us the probability of being male and female, and expand it to consider the beardedness aspect. We know that there are 12 males, 4 of which are bearded, so we can say, given that you are male, the probability of you being bearded is 4 over 12, which is 0.333. We can show this as a conditional probability, the vertical line representing the conditional probability. We read this as the the probability of being bearded given that you are male is 0.333. So we can work out now the probability of selecting someone who's both male and bearded in the room by multiplying each of the relevant branches, which is in this instance 0.6 times by 0.3333, giving 0.2. Now you may notice that this is the same probability as we got for the probability of being bearded, but these are the same only because we did not have any bearded females. If we had had any bearded females as well, the two results would have been different. Finally, I'd like you to notice that we can express that P male and bearded as equal to the two probabilities that we worked out along that branch simply using a probability equation, as you can see there in the bottom right hand corner. Right, now let's move to a more useful example of this technique of probability trees. So here is a screening example, which is a typical use of probability trees. So we have 0.1% of the population, that is 1 in 1,000, carry a faulty gene, which means that the person is predisposed to some nasty disease. We also have a test that detects whether this person has the gene or not. And in people who actually have the gene, the test gives us a 90% reliable reading. That is 0.9% probability of giving us a positive result if the person has the gene. In people who don't have the gene, however, the test provides a positive result with probability 0.01. That is, 1% of the time we get an incorrect positive result. We're going to let G equal a person that carries the gene. P is the test when it is positive, and N is the test when it is negative for the gene. And here is information in the form of a probability tree. We can see that G is the branch with the faulty gene and G' is the branch without one. We can say that the probability of having a positive test back from a person who has the gene is equivalent to 9 times in 10,000. That's 0.0009. Remember, this is taking into account the fact that we start with the probability that the gene only occurs in 1 in 1,000 people, as you can see. We also have two errors representing the false positive and false negatives, and it's interesting to notice that adding up these two values we have a higher value than we did for the true positive result. Returning back to the specific branches, we have a probability of a positive result given that you have a gene of 0.9, which is a 90% chance of a positive test given they carry the gene. What would be nice is to know the probability the other way round, that is the probability of having the gene given that you have a positive test result. And by using the equation, the probability equation I presented in the previous slide, we can achieve this. First, we need to find the probability though of having a positive test regardless of your gene status. This is just the values at the end of two of the branches added together. We can plug these values then into the equation, and then we get the value we need. So probability of having the gene given that they have a positive test is 0.0826. That is, those who test positively actually only have an 8% chance of having the gene. So that's less than 1 in 10 chance of having the gene even if you get a positive result. This figure may appear very low, but it's because we have a number of false positives. Nearly 1 in every 100 is a false positive, you notice, and the prevalence of the gene is very low. So despite the high accuracy of the test, we end up with a low probability of someone having the gene with a positive test. The important thing besides that digression is to realise that order is important when it comes to conditional probabilities. The probability of a positive test given that the person carries the gene is not equal to the probability of the person carrying the gene given that they have a positive test. That is, 0.9 does not equal 0.0826. Now obviously this approach can be applied to other things besides genetic tests. Let's look at another example quickly. Here is the example that's often seen in books, is diseases and tests. So you have a disease and you have a test. And the tests can be in-house tests based upon small numbers of people, large number of people, or even screening tests. They can all be analysed using the same framework. We can also think of this at a more abstract level. We can think of obtaining a summary value from some data set, that is a sample, which I don't want to talk about too much now, like the mean, standard deviation, chi-square value or t-value, and compare that with the chances of getting a specific value, the same summary statistic, from a larger group called the population, which I will call the hypothesized value. We can look at this in terms of our probability tree, that is, what is the probability of obtaining the hypothesized summary value given the value obtained from our data set, as you see in the first example there. And we could also look at it the other way around. What is the probability of obtaining a specific summary value given a specified hypothesized value? Now, as you know, in conditional probabilities all that matters, and in this situation it's no different. These two conditional probabilities are not equivalent. That is vitally important. Most people, when they carry out experiments, they like to know the probability of their hypothesized value given the summary value in our sample. This being represented by the first situation. Unfortunately, the p-value is concerned with the second situation, the probability of obtaining a summary value from our sample given the hypothesized value. That is vitally important. It is the second one, the p-value, not the first one. But the p-value does more than that by considering a range of outcomes for a summary value. Specifically, it provides the probability of a value more extreme than that observed. So let's consider this again by adding the two concepts together. So here we have the idea of combining conditional probability and multiple outcomes to create what is in fact a p-value. Here we have a particular probability distribution for a summary statistic known as a chi-square value, and for various reasons it is for a sample of size 10 of independent observations. The curve provides the distribution of probabilities given that the actual value is equal to 0. Say we obtained a chi-square value of 15 in our sample. We would work out the probability of obtaining any chi-square value more extreme than this from a population with a chi-square value of 0 by working out the area, the blue bit. And this represents a value of 0.0909, and this is a p-value. This is, in this instance, a p-value where it's representing the probability of an observed chi-square value of 15 or one more extreme given that the value is equal to 0 in the population. The important thing is to realize that a p-value is a conditional probability which also considers a range of outcomes. So, in summary, a probability is at any one time all the probabilities combined are equal to 1. A probability histogram provides the total area under the curve which also equals 1. Therefore you can calculate specific areas which equal probabilities representing sets of outcomes, and specifically we can consider the more extreme than X situation. The importance of considering conditional probability where order matters was highlighted, and the screening example where there was a greater chance of having a positive test result than having the condition, which was fictitious data by the way, but it does represent reality in some screening circumstances. And finally, all this allows us to appreciate the fact that the p-value is a conditional probability which considers a range of values. But we've only looked at the first of the four aspects of the p-value. We can move on to the second aspect now, that of sampling, where we'll see how the p-value is affected by the sampling type, specifically the sample size, and the importance of understanding the difference between a sample and a population to further understand what I meant by the terms summary statistic and hypothesized value when I was discussing the conditional probability aspects. Bye for now.